Our topic for today are congruences, and we'll be quite busy in this section, so let's start immediately. So definition, and that's a definition that we know from last section, and that is definition. So let A be integers, and then n is in Z plus, and we define A congruent B modulo n if and only if n divides B minus A. We saw examples with 5, 6, it could be done for any number n. Actually, I should be even say n is greater or equal to 2, because no one is interested in relation modulo 1. Modulo 2, that's again somewhat interesting. So, since I have problems with my markers, let me bring that here. So, here are the properties. So, first theorem. So, we have lots of theorems today. 6.4.1. And it says the following. The following are equivalent. This is standard acronym we use in mathematics. So, it's what? A is equivalent with B modulo n. Number 2, B equals A plus Kn for some K in Z. Wow, this marker is great. And A and B have the same remainder. Modulo n, which means what? A mod n, that's how we label the remainders. A mod n is equal B mod. Although, I must admit, this is the official notation we introduced. I'm more used to the notation remainder of A modulo n equals remainder of B modulo n. I think it's a better notation for our class because mod will show up anyway, so it might be a little confusing. All right, so how do we prove this? 1, 2, 2, 3. Very often in mathematics, when we prove that statements are equivalent, we have a chain to use transitivities. It will be like this. 1 implies 2, 2 implies 3, and then 3 implies 1. I don't need to say that to prove that I implies 3 because it's transitivity of implication. So because of that, this is true. So how do I prove that? So 1 implies 2. It's actually exactly by definition A equivalent with B modulo n by definition. So assume A congruent with B modulo n. By definition, that means n divides B minus A, which by definition of divisibility, that means B minus A equals K times n for some K in Z. Solve for B. B equals A plus Kn for some K in Z. That's exactly what 2 says. What about 2 implies 3? What? So now I will assume that B equals A plus Kn. And let us assume that the remainder of A modulo n is R. And then this is just a little review of what we had in that section. What would that mean? That would mean that what? By definition of remainder, A equals Qn plus R, where R is less than or equal less than n. And every number satisfying that is a remainder. But then what? How much is B then? B, it says A plus Kn, so it's Qn plus R plus Kn. I get these two together. Q plus K times n plus R, where R is between 0 and n by definition of a remainder. That's remainder for B as well. So implies by definition that remainder of B B modulo n is R. All right, collect little markers so that I can at least do some colors. So I see we started from remainder A to be R, we got remainder B to be R, so they are equal. And then how do we prove that 3 implies 1? 3 implies 1. What does it say? So assume that the remainder of A modulo n equals remainder of B modulo n equals, I'll call that number R. Nothing special about that R. So what do I know? A equals Qn plus R. B equals Q1 n plus R. And then what? Then I have B minus A. R and R cancel. So I'll get Q1n minus Qn, which is n times Q1 minus Q, so n divides B minus A. Here it is. So we proved that all these three are equivalent. When we have many statements like this in our course, what is the value of these theorems? Value of these theorems is that whenever we establish a fact in one of these three forms, we can just pop up the other two if they are more convenient for our work. So that is really very, very convenient. All right, so that's our first progress. Let's see what else. So we'll need to learn a lot to be able to get what we need. By the way, what? Remark. Because of this, that everybody saw if A is congruent with B modulo n, then B looks like A plus Kn. That's why the class of all B's that are equivalent, so A class, which is class set of all B's, such that A is congruent with B. Very often we say that's A plus KZ. Z stands for MZ. If it's modulo n. Z stands for that arbitrary K. So it says, how do you get class of A? Take A and then add any multiple of n. So NZ means pick any element from Z, multiply by n, and add it up. All right, now we want to do something interesting, and that is we want to establish a little algebra between the class. So let's see how that works. That's what next theorem is telling us. So in that statement, we want the following proposition. Says the following. Number one, if A is congruent with C modulo n, no B, and C is congruent with B modulo n, and then A plus C is congruent with B plus B modulo n. And the second, the same thing for multiplication. Why is this crucial? Because it says that actually this congruence behaves like equal sign. We can just solve the equations and do many things that we are used to do. So proof is fairly easy. What? How do I write the proof? So if A is congruent with B mod n, that means that B equals A plus K. C congruent with D mod n, that means that D is congruent with, D is equal, sorry, C plus L. So I cannot assume that they're the same integer according to the previous theorem. Then what? If I add them up, I'll get B plus D equals A plus C plus k plus ln. So that's why these are, so a plus c is congruent with b plus d modulo n, because this is the multiple. Also, if I multiply them, what do I get? B times d is a plus k n c plus ln are 4, and then I get ac plus aln plus kcn plus kln squared. Obviously, this is a multiple of n. This is n times u, so ac plus n times u, because I can factor out n. So ac is congruent with bd modulo n. So it's very easy proof, but it is very important fact, because of this fact, we can actually calculate remainders in a much more efficient way. So here is actually one interesting example, 641. It's really curiosity to see that working, and then also it's very useful. So here it is, we want to calculate.
Hi.
Yes.
Is this are you chemistry?
When does your class start?
10:30.
10:30, then probably I should stop here. Thank you. All right, let's continue. Example 641. Calculate 675 to the power 307 mod 713. What's happening? It's a huge number, so your calculator cannot, it's beyond the memory of your calculator. So it's a huge number, but now our idea is not to calculate the number itself, but to see when I divide it by 713, how to find the remainder. So here's the idea. You can always, you remember how, now this is more complicated. If you look at those states in the partition, there are some 713 states. And then what? The good news is whenever you get a result, you can always trade it with whoever is in the same state for calculation purposes of the remainder. And that's what we do. As soon as we get a huge number, we go down to the smaller remainder, and then at the end we just add or multiply these remainders and we get the result. Generally, here is the idea, how we can even organize this process even more. And you'll see in a moment why. We'll write first 307 in a binary system. Doesn't have to go that way, but it helps. It's 256 plus 32 plus 16 plus 2 plus 1. If you want, you can do it in ternary system. It doesn't have to be binary. But binary kind of doesn't leave too many holes, and the results are not too big, actually. No, that's more important. And then what? We'll say the following. All right, 675 to the 307 is actually this. 675 to the 256 times 675 to 32 times 675 to 16 times 675 squared, and then times 675. This is according to the properties of multiplication. If you multiply these powers, that's the same as adding the exponents. And now what? We'll calculate on the sides all these powers of 2. So 675 squared is congruent with 18 modulo 713. How did I get to that, by the way? So here it is. Let me show you how you can use calculators to get this, unless you have a feature of a machine that does remainders. So I'll do the following. I'll take 675, I raise it to the square, and I got some numbers. So 675, how did I get this? 675 squared is 455,625. Then I divided that by 713. Divide by 713, and I got 6,000 639.025,245, something like that. 1025,2454. But generally what? This is the quotient, and this is the remainder, but in the fractional form. So I'll do the following. I'll take 675 squared minus 639 times 713. Or you know what I'll do? No. I will take this result from the calculator and I'll subtract 639, and that will give me 0.0252454. So minus 639, and I got this. And this is what? Something over 713. So when I multiply it by 713, it will tell me what the remainder is. Times 713, and I'll get 18. Why? Because generally I know that this represents something over 713. So to recover what something, I just multiply by 713, and I got remainder 18. And then the same way, now what? 675 to the fourth. What's that? That's 675 squared and then squared again. But 675 squared is in the same state as 18, so I can replace that whole arc here. So you can always replace a huge number with someone from the same state. So after 675 squared from the previous line to 18, so we know that this is 324. Now 675 to the 8th will be square of the previous one, so I'll just say immediately congruent with less writing, 324 squared. And then I'll do this business. I will take that square, divide by 713. When I get the quotient, remove the quotient. What's left, multiply by 713. And this is congruent. And I just copy the results from the book, from the notes, and that would be 165. Then 675 to the 16. I don't need, I do need 16. I didn't need 8, but I needed to read 16. We want 165 squared, so square the previous line. That's where base 2 comes. So that would be 1675 to 16 would be 165 squared, and that's 131. Then 75 to 32 would be 131 squared, and that's congruent to 49. I'm not writing the index, we all know that it's 713. Then 675 to 64 is congruent with 49 squared, and that's 262. 675 to 128 is congruent with 262 squared, which is congruent with 196. And finally 675 to 256 is congruent with 196 squared, and then using this procedure we get that that's 627. Now what? So I have all the pieces, I don't need all of them. Which one do I need? 256, which is this number. 32, which is this number. I need power 16, which is this number. I need power 2, which is this number. And 675 itself. So generally what? We can assemble them. So we'll say the following. 675 to 307 is congruent with 627 times 49 times 131 times 18 times 675. And then what? If that exceeds your calculator abilities, then what you can do is multiply these to reduce, the same way modulo, multiply these to reduce. Either way, actually the way I did, no, just when you do the reduction, it's congruent modulo 713 by 3. Actually, let me try, although you cannot see this probably, or maybe I can actually get this. Let's hope that this is readable. So it's what? 6, usually in our class if we have document camera, I would show this better, times 49 times 131 times 18 times 675, and I'll divide by 713. 627, 49, 131, 18, 675. Oh, we did rounding, and that's what's dangerous sometimes with the calculators. So I have to do it piece by piece. A second and 3. Let me clear this. So I got 627 times 49 times 18. I'll take these 3. Divide by 713. Remove 775. Multiply by 713. And I got 439. So for these 3, I got 439. So 627, let me make sure that I know which ones I entered because I changed plans. 627, 49, and 18. So these 3 gave me that result. Then I'll go 131 times 675, and I'll divide by 713. Subtract 124, multiply by 713, and I got 13. I got 13 from these two. I got 439 by those. Now it's easy. 439 times 13 divided by 713. I subtract 8. I'll multiply by 713, and I got 3. This is not equal, it's congruent. So, using nice properties of this relation, we are able to calculate modulo of very high powers using this trick. And then you can see a couple of homework problems of this type. And then here's another progress that we can make in this direction, and this is the theorem that we actually kind of announced when we studied Euclidean algorithm, and that theorem says the following. Theorem 643. It says the following: let A, B belongs to C if GCD of A and B equals N, then there exist U and V from Z such that AU plus BV equals D. Actually, this theorem is related to that problem that was on exam 2, where I asked you set A was actually set like 3Z divisible by 3, set B was 5Z. And I asked you if the set of, and C was AU plus BV, where what, which would be actually, no, C is set of 3U plus 5V, where U and V are integer, and I ask you, is C equals Z? And since 3 and 3 are relatively prime, this theorem says this must happen. And of course, we did it there in a more specific way, but this is generally famous theorem, and it is true. Let me raise this as a reminder. So what would that be? A real proof would go by induction on the length of the proof. Generally, the whole idea is the following. Let's say that, let's use a proof. If you look at Euclidean algorithm, for A and B, and it looks like this. A equals Q1B plus R1. Then B equals Q Q2R1 plus R2, and then let's say that Rn, or let me see for indexing, R1 equals Q3R2 plus R3. So if it's Rn here, Q has twice bigger index, so it would be Qn plus 2, Rn plus 1, and let's say there's no remainder. So previous line is what? Rn minus 1 equals Qn plus 1, Rn plus Rn plus 1, and remember the last non-zero remainder, that's your D. So generally what? A real proof would go induction on N, but let me give you a procedure that actually shows what's really happening, and basically that's the induction step. So you go from the bottom up. So first line says the following: D equals, let me make these red, because these are like vectors in a vector space analysis. And these are just coefficients. So D equals, how can I write it? Rn minus 1 minus Qn plus 1 Rn. So look who are my vectors. Rn minus 1 and Rn. Then from the previous line that's missing here actually, then I trade the one with a higher index. This is Rn. So Rn could be traded from the previous line that's missing here. Let me write it there. So what would be the previous line? Rn minus 2 equals Qn Rn minus 1 plus Rn. So here you trade Rn as what? Rn equals Rn minus 2 minus Qn Rn minus 1. So when I traded that, what do I get? Rn minus 1 minus Qn plus 1. Rn could be traded as Rn minus 2 minus Qn Rn minus 1. Never execute multiplication on R's, on those red ones. Do all the calculations with coefficients, but not with vectors. So it's Rn minus 1 minus Qn plus 1 Rn minus 2, and plus Qn plus 1 Qn Rn minus 1. And then these two could be combined, so it would be what? 1 plus Qn plus 1 Qn Rn minus 1 minus Qn plus 1 Rn minus 2. So what happened? Now I have the other members, n minus 1 and n minus 2. Who is younger among them? This guy is younger, he has higher index, so he could be traded using next line, and so on. At the end, when you continue this, at the end you will express everything with two oldest members, two guys in the beginning of the story, which is A, B. And that's basically a proof. As I said, I could have done it using induction, but I think this is telling you more how things should be done. And let's just do this specific example that actually reports that. So this example says 642. It says the following. Actually 642 will say the following: find the multiplicative inverse of 43 modulo 660. What? First, what is multiplicative inverse? We wrote multiplicative inverse modulo 660. So multiplicative inverse means two things should be multiplied to give me one. But not exactly one. It says modulo 660, so congruent here is 660. And then multiplicative inverse of a particular number, which one is it? 43. And they want this x, that 43 times x is congruent with 1 modulo 660. Why would we need that? We'll see that in a moment. So the question is, how can we do it? And the second one, how? If we can, how can we do it? First answer is yes. Because 43 is a relatively prime for 660. That's easy to see. And now what we'll do, we'll actually use the construction from a minute ago and do the following. We'll do Euclidean algorithm. So we'll do the following. 660 equals 43, let me do that red. 660 is like a vector. Equals, I divide 660 by 43, I get 15. And I get remainder 15. On the next line, you continue with the red ones. 43 equals, that's easy to calculate now, 2 times 15 and plus 13. Now I got 15 equals 1 times 13 and plus 2. And then 13 equals 6 times 2 and plus 1. And that's it. That's the last non-zero remainder because 2 is multiple of 1. So this is GCD from a minute ago. Since they are relatively prime, I'm not surprised that that's 1. So what did we say a minute ago? Now you go backwards. And you say the following. 1 equals 13 minus 6 times 2 equals. Now you want, 2 is the younger one of those, appeared later. So 2 is now traded. How do you trade 2 from this line? So you read that 2 equals 15 minus 1 times 13. And that's where you trade. 13 minus 6 times 15 minus 1 times 13. Never multiply red numbers, just black ones. So in algebra, it's 13 minus 6 times 15, minus 6 times minus 1 is plus 6, I multiply them, plus 6 times 13. So I get 6 times 13 and 13 is 7 times 13, minus 6 times 15. By the way, I can check it, this 91 minus 90 is 1, so it's all good. Now what do we do? Who's younger here? 13. So 13 should be traded here, so what's 13? Is what? 43 minus 2 times 15. And then I trade 7 times 43 minus 2 times 15 and minus 6 times 15. If I multiply, I get 7 times 43 minus 20 times 15. How did I get that? 7 black ones could be multiplied. 7 minus 14 and minus 6 is minus 20. Now what do? I finally trade 15. So 15 is traded as what? 15 equals 660 minus 15 times 43. And when I trade that, I get 7 times 43 minus 20 times 660 minus 15 times 43 should be right. 43. And then if I distribute the black numbers on 43, I'll get minus 20 times minus 15 is 300, 307 times 43 minus 20 times 660. Let me check my calculation. 307, yes. Now what? But how is this answering our question 43 times x is congruent with 1? Look at this. This is the multiple of 660. So if you look modulo 660, that's generally, that's a 0, because that's in the class of 0. So this is congruent with 0. So generally what we have is the following, that 1 is congruent modulo 660 with 307 times 43. So what is that telling us? That x that we are looking for, x is 307. So this is how we can find multiplicative inverse for certain module, if, of course, our number is relatively prime to that module. This is an important construction for what we'll do in our next few constructions. So it's worth memorizing. It's a famous construction used heavily in algebra, in programming, and in many mathematical constructions. We continue our discussion of congruences. Let me record one famous theorem about congruences, and that one we'll use for some cryptography at the end of the section. So it says the following, Theorem 645. It says the following: let P and Q be two distinct prime numbers. And let A be an integer. A not divisible, P does not divide A, and Q does not divide A. Then we have the following. A to the P minus 1 is congruent with 1 modulo P. And the second one, A to the P minus 1, Q minus 1 is congruent with 1 modulo PQ. The top one is the famous Fermat's theorem, little Fermat's theorem. This is little. Little Fermat's theorem, because there is a big one that was famous, long-standing open problem. So, and that's why people call this one little one, although this one is important theorem with lots of applications. So generally, before I do the proof, let me illustrate what is this telling us. So for example, if I need to calculate 7 to the 260, and if I want 7, no, this is not a prime, I'll have to change that. 7 to, let's say, 42. And if I wanted modulo 43, I have no dilemmas. 7 to the 42 is congruent with 1 modulo 43. Why? Because 43 is a prime, here is 42, and 7 is not divisible by 43. So it all matches, so little Fermat's theorem says remainder is 1. What is the idea of the proof? The idea says the following. Let me look at the numbers a times 1, a times 2, up to a times p minus 1. These numbers, and that's not maybe obvious, but it's fairly easy to prove, that each of them is congruent with the different numbers. So it's congruent with some number I1, congruent with I2, congruent with IP minus 1. I don't know what they are, but I know that they are not congruent. So basically these numbers, I don't know in which order, are basically again 1, 2, 3 to pi p minus 1. I don't know which one of them is 1, but since they are not congruent among themselves, then they are different, they have different remainders modulo p. And then what if I multiply modulo p? If I multiply left and right sides, what happens? I get a to the p minus 1, because a is repeated p minus 1 times 1 times 2 times p minus 1 is congruent. Now I have I1 times I2 times I p minus 1. I don't know which one is which, but for product it doesn't matter. They are basically product of first p minus 1 numbers. And then what happens if I cancel, and I can cancel congruences if the number is relatively prime to the index. I'm again using another property that we didn't prove over here. We get, but it's easy to prove, a to the p minus 1 is congruent with 1 modulo p. And then part 2 is proved in a very similar way or using the first rule. And then what? Let me show you an interesting way how we can use this property actually for the coding using primes. So what would that be? So cryptography, a little bit of cryptography, really nothing that can be called serious cryptography. But cryptography. What we have there is just we are transferring some sequence of symbols. Let me call these symbols C1, C2 up to Cn. And then we are afraid that that this communication might be intercepted by the enemy, and then we just use some coding function and that produces f of C1, f of C2, and f of Cn. And then what? When this message is sent through insecure channel, then someone might get that coded this coded message. But in order to get the original message, one needs to have an inverse for that process, and if the coding is done in a skillful way, then inverse process is not so easy to organize. Actually, inverse process is actually breaking the code. So the simple one is Caesar's cipher. So what? So for example, if we have example 643. Here what we did. What we replace letter by their rank. Now we add a fixed number. So let's say we are adding 5 modulo 26. That's what I wanted to see. So there was this tech, and tech, according to the order of these letters in the alphabet, is 20, E is 5th in the order, and X is 24. And then what simple coding would be to add 5 to each of them. So that's that coding, so we'd get plus 5. That's Caesar's technique, 25, 10, 29, but we added modulo 26 because there are 26 letters. So 24 and 5 will not be 29, that will be 3. So then 25, 10, 3, if we look at the 25th, 10th, and 3rd letter, we'll let YJC. So that's the coded word. So that's the word that's sent, and then of course any serious hacker would break that easily. But if we want to recover the word, then we would need to reverse the procedure. So recognize them as 25th, 10th, and 3rd, subtract 5, and then get the word 10. There's a whole theory about it, how to choose the coding, and then how to recognize frequency of letters in the word. So that's a separate discipline, and many of you might see it in your computer science education. Here we just want to connect with congruences, how this could be used. And then, so here's one interesting technique, and generally, before we even express the problem and how to use the coding, let me do one example that actually repeats what it did in the previous section. So I'll just record the result. Example 644. Let us find, for whatever reason, I'm not explaining it now, what is the inverse of 5 modulo 72. So we want to solve the following equation, 5x congruent with 1 modulo 72, and then we explained last time we use Euclidean algorithm, and then the section, or actually the same section earlier in this section. and get actually that 5 times 29 is congruent with 1 modulo 72, and then 29 is actually the inverse. 29 is the inverse of 5 modulo 72. All right, then what do we do? Let me try the black pen again. It's completely bad. Oh, there's another. So what do we do? Now it is the following. Suppose, so here is the idea of the coding. Idea of coding. We use module 95. Why that one? You can, for any practical purposes, you use a much bigger number. This is just for illustration purposes. The whole idea is that it's product of 2 primes. 5 times 19, both primes. Okay. And then what? The idea is the following one. According to the theorem that we saw a minute ago, if P does not divide A, and Q does not divide A to the P minus 1, Q minus 1 will be congruent to 1 modulo PQ. In this case, P and Q are 5 and 19, we'll get that A to 4 times 18, 5 minus 1, 19 minus 1, is congruent with 1 modulo 95. So generally it tells us that A to the 72 is congruent with 1 modulo 95. That's why in this previous example I solved this problem on of inverse modulo 72. So how will all that play? So here's the coding procedure. So here's example. Someone coded a secret digit. A digit A between 1 and 94 by raising it to the 5th power. So that person did A to the 5th. Reduced modulo 95, like we did in Caesar cipher, and got the result 27. So 27 is coded the version of A. My question is, can we break the code? Can we recover A? So generally what? You can say the following. Oh, if I were able to take a 5th root, but there's no 5th root among the integers. But instead of going down, we actually want to go up. We'll say the following. Let me try, because I cannot go backwards. Let me try to raise both sides to some k, which I don't know what is. So that actually that 5 gets erased. That's surprising in calculus or in real numbers, in integers, but actually modular calculation it's not. Why? Because here it is. Look at this. Let us choose k such that 5k is congruent with 1 modulo 72. And you will see in a moment why. By the way, I already prepared for that, which means, according to the previous example, k equals 29. Why is 29 the key? 29 is really playing like a role of the 5th root. Why? Because here it is. A to the 5th to the 29 is congruent with 2 to the 29 modulo 95. But then what happens? So it looks even worse. Here it says 5 times 29. So instead of getting lower power, I got higher power. But generally what? 5 times 29 is congruent. It says 5 times 29 is congruent with 1 modulo 72. That means that 5 times 29 equals 72q plus 1. So this will be 8, I don't care how much is that q. And that's what? 8 to the 72q times 8 to the 1. 8 to the 72q is 8 to the 72 to the q times 8 to the 1. But 8 to the 72 is 1, that's why I wanted multiples of 72. So this is just 1 to the q times 8 to the 1 and just congruent with a. So generally multiplying by 29 creates a few 72s, I don't care about them because they produce 1 modulo 95. This is all modulo 95. And they actually erase that extra power and give me back power 1, and that's what we want. So this is the recovery. So solution is A is congruent with what? Because this gives me just A. With 2 to the 29 modulo 95. And then with the way we explained earlier today, how do we calculate the powers? We not 2, sorry, this is 27, I read this wrong. 27, just so 2, so 27, 29. And that's what's left, is to calculate how much is 27 to the 29 modulo 95, and I will finish it here because I have no space, so let me erase this. And all this. So generally 27 to 29, let's calculate. So A is congruent with 27 to the 29 modulo 95. So how did we do that? We say 29 powers of 2, 2 to the 4th, which is 16, plus 2 to the 3rd, which is 8. So this is what? 16, 8, 24, plus 2 squared, 24, 28, and 1. So generally, 29 to the 1 is just 29. I don't need 29 squared, because I need 29 to the 4, 8, 16, but I have to calculate it, and the way we, what's 27? Sorry, 29 is fine, 27 to the 1st. I'm raising 27 to these powers. 27 to the square is congruent with 64 modulo 95. 27 to the 4th is congruent modulo 95 when I square 64 squared. And that gives me 11. 27 to the 8th is congruent with 11 squared modulo 95. That one you can calculate even by hand. That's 26. 27 to the 16th is congruent modulo 95 with 11. And then what? The same way as we did earlier today, I need 16, which is this guy. I need 8, which is this guy. I need 4th power, which is this guy, and just 27 here. So I get what? That A is congruent with 29 times 11 times 26 times another 11 modulo 95. And when you reduce it modulo 95, you get 12. 27, sorry, this is 27. 11 times 11. So 37, 29 are close, but I shouldn't mix them up. So 27 is in the base, and then 29 was broken into the these powers, and then we're repeating it here. And generally what? Of course, you can test this result, so test it. So if you take 12 and you raise it to power 5, because that's what we decoded. Someone was coded to power 5 and it gave us 27. We said it's 12. If you try 12 to the 5th and you raise it modulo 95 and you reduce it, you should get 27. Just to check work. So that's one nice application of this congruence theory to encryption. So once again, let me emphasize that's probably the trickiest thing. There are two congruences that you run. So on the ground, you run congruence modulo 95, which is PQ. But in the exponent, because you get P minus 1 times Q minus 1, which is 72, you run congruence modulo 72. So you reduce exponents modulo 72, but then because whatever's multiple of 72 will produce no effect on the base A, but then whatever's after that, the remainder after that, that will be used to finish your calculation. So modulo 72 on top in the exponent and modulo 95 on the ground.